Hi, I thought we'd start this lesson with a photograph of one of my favourite places. This is the Scottish Highlands. And the reason I've shown you this picture is because the Scottish Highlands are the largest extent of metamorphic rocks that we find in the British Isles. These are old and very varied metamorphic rocks that have formed in a number of different ways. And it sort of ties in with what today's lesson is all about. Because what I want to look at today are the conditions in which metamorphic rocks form. In particular, the relationship between temperature and pressure. We're working in our purple Theme 6 booklets. We're working on pages 5, 6, and 7 today. You will need some colouring pencils. Okay then, let's go. This is a map of the Highlands. Each of the different colours on this map shows us a different type of metamorphism. We tend to define these by the minerals that we find within them, because we'll find some minerals that form at high temperatures and pressures, and other minerals that form at low temperatures and pressures. You can see on this map that the blue and the red colours, which take up most of the highlands, are the higher temperature and pressure minerals. The sort of green and yellow minerals, or areas on this map, sorry, are the lower temperature and pressure minerals. So we can see that there's a variety here. There's also a difference in the type of metamorphism. Most of the Scottish Highlands is formed by what we call regional metamorphism, where the whole area, thousands of square kilometres here, has been buried to a depth of maybe 10, 15, even 20 kilometres in places. By being buried to that depth, they get put under a huge amount of pressure and also very high temperatures. And that combination will metamorphose, it'll change the rock. But it's not the only way that rocks get metamorphosed in the Scottish Highlands. We can also have what we call contact or thermal metamorphism. And this is caused by the intrusion of plutons. So, for example, if we get a big granite pluton intruding into some country rock, often sedimentary rock, the heat from that intrusion will spread out into that surrounding country rock and it'll metamorphose it. The closer the rock is to the edge of the pluton, what we call the contact, the more it'll be metamorphosed because there's going to be more heat. As the heat dissipates, as it moves away from the granite intrusion, that the amount of metamorphism will decrease until eventually we get to a point where rocks haven't been metamorphosed at all. The country rock is it what it was originally. This zone of metamorphism around a pluton we call a metamorphic aureole. We're going to talk more about aureoles in a subsequent lesson. But we've got these two types of metamorphism. Regional, where pressure and temperature are the big agents of metamorphism. And we've got contact, or thermal metamorphism, where it's heat that's the agent of metamorphism. And we don't have the rocks under pressure. Now we can tell what type of metamorphism from the rocks that are formed. At the bottom of page 5 here, I've given you two diagrams of the two different types of metamorphic rock. On the left there we have a metamorphic rock that's formed by thermal or contact metamorphism. On the right, a rock that's formed by regional metamorphism. What I'd like you to do is I'd like you to try and spot the difference between these. What do we notice in the texture of these two rocks that's different? Have a go at that now. See what you can come up with. Okay. When we look at these two rocks, there's one, I think, massive clear difference. And it's this idea of foliation. The rock on the right is foliated. If you look at the mica crystals there, they're aligned. Now, the garnet crystal has grown within that rock and it's sort of pushed the sheets of mica apart, but there is an alignment in that rock. That alignment is there because of the pressure. So the pressure was acting on this particular rock from top to bottom. So the mica crystals have grown at right angles to that, like we saw with the starburst suites. So that regional metamorphic rock has been formed under very high pressure. We can also see, though, that new crystals have grown in this particular rock, like garnet, for example. Garnet is an exclusively metamorphic mineral. It only forms in metamorphic conditions. So we know that this rock has been subject to high heat and high pressure. The rock on the left, though, you'll notice doesn't have that foliation. There is no alignment of the crystals within there. In fact, it just looks like the crystals here have been sort of squidged together. Now, this tells us that this rock has been heated. Not enough to make it melt, like we saw with the starburst, but enough to squidge them together. And the way we can recognise this is that we start to spot 120-degree angles between the crystal faces here. I've highlighted 3 of them. Can you find any more and highlight those on your diagram? So this difference between non-foliated rocks that are formed by heat and foliated rocks that are formed by pressure and heat is key to understanding how they form. Okay. Let's have a look at, I think, the most important graph in geology, the one that really shows us where all the different types of rocks form. You've got a copy of this graph on page 6 of your Theme 6 booklet. First thing I want us to do is do a little colouring in together, okay? Because I want us to understand what the different areas on this graph mean. With this graph, we have 2 axes. We've got a horizontal axis, which is temperature, lowest at the left, highest at the right. But our vertical axis here, we've actually got 2 sets of labels on there. We've got depth and we've got pressure. Now, the reason for that is that these 2 are proportional. In geology, they are the same thing. The deeper that you go, the more the pressure increases. Okay, let's do some colouring in. Let's start over on the right here. This area, at very high temperature and also high pressure, marked by the partial melting curve there, represents where igneous rocks form. So all the area I've shaded in red there is pressures and temperatures where rocks will melt and we get igneous rocks. Colour that in, label it up on your graph. The second area I want to shade in here is at the top left there. So this is low pressure and low temperature. The rocks that form there are sedimentary rocks. So get relatively low depths, a few kilometers maybe, temperatures that are, you know, cooking temperatures or less, and that's where we have sedimentary rocks form. Again, colour that area in. You do need to draw in the curve there. I'm afraid it's been left off the graph, and label it up. The third area I want to colour in is the grey area there. You see there's a curve there marked limit of metamorphism. Those conditions don't exist. They don't exist naturally on Earth. You cannot have pressure that high at temperatures that are that low. It just doesn't happen. So there are no rocks at all that form within that grey area. What we're left with in the middle, this wide range of temperatures, this very wide range of pressures, is metamorphic rocks. This is one of the reasons that metamorphic rocks are potentially a little bit tricky, because there is such a wide range of pressures and temperatures at which they'll form. I want to colour these in a bit as well, though. Okay, so at relatively low temperatures and moderate pressures, we have our metamorphic rocks there, are what we call low-grade metamorphic rocks. At slightly higher temperatures and higher pressures, so we're going from about 325 up to about 550 degrees centigrade there. Those are medium grain metamorphic rocks. And finally, at the higher pressures and higher temperatures, we've got our high grade metamorphic rocks. Notice as well, there are two zones of metamorphism. We have our contact metamorphism, which is at the top. So we have low pressure and increasingly high temperatures there. And then where we have higher pressures, and with them then higher temperatures, we have what we call regional metamorphism. Make sure you've got your graph labelled up. And of course, it's important to remember that more temperature and more pressure means more metamorphism, and we describe that as a higher metamorphic grade. Okay. What I'd like you to do now on your coloured in graph is in the circles that I've given you, I would like you to label up where you think you'd find each of the rocks that are listed in question 3b at the top of page 6. Okay, what conditions would they form in? I'd also like you to think about, for the metamorphic rocks, what their parent rock might be. What did they start out as? Okay. Now's the time to press pause and have a go at that question. See what you come up with.